Thank you very much. Thanks for the invitation to talk in this workshop. It was a little bit of a last-minute, maybe, invitation, and so I struggled a little bit to think about what I could talk about for many-body quantum systems. It's not really my usual stuff, but actually we had a project that was ongoing and that I thought could be a good fit. So it would be something a bit different, not really quantum computing oriented, but some applications to the many-body quantum systems using Tensor-Trains, which is what we mathematicians call matrix product states. So in a somewhat unusual twist for mathematicians, there are actually quite a few co-authors on this paper over here. So I would like to thank all of them for inviting me into this project that we are now continuing, especially with Misong Dupuis, in this direction of many-body systems. So I don't think there is much introduction needed, but nevertheless, I wanted to point out that the reason to use matrix product states is because in the absence of a working quantum computer, let's say, it is good to have some tools that are able to tackle really high-dimensional problems, like finding the many-body states of, for example, a quantum spin chain like this, where essentially the unknown could have value plus or minus 1 on each of these sites, but the problem scales exponentially with the number of sites to the 2 to the power n. And so it has become somewhat routine to explore these kind of one-dimensional problems using the Tensor-Train format or matrix product states, where we write essentially a many-body wave function by using approximately, maybe, using a product of such objects. So for a given sigma 1, sigma 2 to sigma n, these guys on the right would be a vector on the left and on the right, and matrices in the middle, such that the product gives you just a scalar as intended to be the entry into this tensor. We've seen yesterday already a couple on the posters and so on this diagram notation. I will try to be a little bit more explicit sometimes. And
what is the cap A's? They are living in what space?
So these are the cores. So this blue object here represented here. So each of these has 3 indices. So for example, this guy over here has index sigma n minus 1. So that's this guy on top. And then 2 bond indices or ranks, as we call them. I'll have to jump a little bit back and forth between the two communities. My language, or I might slip also sometimes. So just be warned. So I might call rank sometimes or bond dimensions. These are the same things. And this will be tractable essentially if we can maintain these ranks to be small. Yes?
So I've only just learned about Tensor-Trains pretty recently. I thought when you wrote it like you in the middle of the page, I thought that in the Tensor-Train format you just have the product of matrices and you don't have a sum over the ranks. I thought you had a sum over the ranks if you do like the canonical tensor decomposition.
So every time you see this notation here, every time you see these links between, this means that we are summing over the indices.
Okay.
So typically, in the Einstein notation, for example, these sums would be omitted because we just assume that as soon as we see a repeated index, we're actually summing over it. But there is a sum.
Okay.
I mean, that is literally just matrix multiplication of one column vector and n minus 1 matrices, right?
Yes. Whenever I select a value for all these sigmas, now I just have matrices and I'm making a product of matrices. I suppose that's where the matrix product state name comes from.
It's amazing that this simple observation should help us with anything.
Absolutely. Yes?
So just to be clear, so the result of the Tensor-Train is a vector, not a scalar?
So the result of the Tensor-Train is a tensor of dimension 2 to the power n in this case.
But when you for
I can select all possible values of sigma, right? And for each of those, I would get a different result.
Yes, but for a specific set of sigmas, the value is a...
Just a scalar, the entry into the tensor. So actually, yeah, so this is something to be to remind also ourselves is that whenever we want to access the entry into the tensor, it's actually an expensive operation in this format. you have to make the whole product in order to access just one entry.
So, Spencer, just graphically can think about it. If we have the bullet that's a scalar, one leg, it's a vector, two legs, it's a matrix, three bonds, you have a three-dimensional tensor. Just graphically.
All right, so these Tensor-Trains, as we call them in the applied math community, have taken a life outside of quantum physics. And for example, they can be used in order to solve some high-dimensional problems that have nothing to do with electrons. For example, this was a kind of toy problem proposed by Christine Tobler in her PhD thesis in 2012. So let's consider this baking sheet on which we have 4 cookies of unknown thermal conductivity. And we would like to solve something as simple as the heat equation, a stationary heat equation. But the little twist, of course, is we would like to be able to solve it for each possible value of the parameter. So the rho parameter here can change. And so instead of doing the computation every choice for these 4 possible ones, we can look for the solution to this problem, which turns immediately into a 6-dimensional object, the distribution of the heat on this cookie sheet. And luckily, with some mild assumptions, the solution to this kind of problems has low ranks. So we can use some iterative linear solvers that exploit this low-rank structure, and we'll be able to solve the problem for all possible values of the parameter at the same time. So that's quite nice. Some say that the point of this matrix product space is to break the curse of dimensionality. Of course, it's not completely true. But for the problems where the solution exhibits this compressible structure, we can use this Tensor-Train format in order to reduce the number of parameters from exponential to linear in n. So I'll just note that there are various tensor decompositions that exist in the literature. So in the diagram format, if we have a tensor of dimension, let's say 4, something like this, we can use what's called the Tucker decomposition in order to reduce the size, say, of each of these bonds. So using something like the SVD, we can reduce the dimension from a large mode parameter to something a little bit more reasonable, say, right? But this kind of decomposition does not break the dimension of the curse of dimensionality because the core of the tensor over there is still of dimension 4. However, in the case of the matrix product states, we'll note that the amount of data that we have is now linear in n, the number of sites, as long, of course, as the ranks stay controlled. The rank can, of course, to represent the entire state space, grow exponentially, and then this property is not true. So for moderately large n, one thing to note is that we cannot ever go back to the full tensor. We cannot extract our tensor, to our matrix product states, expand it into a full tensor to do some operation. It's completely unfeasible, so it's important for this kind of computation that we start in this matrix product states format. We perform the arithmetic within this format, and we keep low ranks the whole time. Otherwise, at some point, we will run out of memory. And if all this happens, then the format will enable us to solve some very high-dimensional problem, like finding the ground state of some spin chains that previously were unable to be explored. So the second side of my talk will concern randomized linear algebra, which is something that has emerged in the last 10, 20 years as something a very different and useful side of numerical linear algebra. So usually for matrices. I'll make a very small detour here. So the first application I saw of this is what's called the randomized trace estimators. So let's say I want to have a matrix A, and I want to compute the density of states. So the the spectral measure of this matrix A, which might be quite large. And I would have to compute this kind of traces for all A. So if I can diagonalize the matrix, then I'm done. But if I cannot, then this can become quite expensive. An alternative is to use the kind of Hutchinson trace estimators where we can take random vectors omega. For example, they can have Gaussian distributed entries, or they can have entries that are plus or minus 1 with a coin flip. We can take a small number of such vectors, take such dot products with the function of the matrix in the middle, and compute the quantity of interest. And as I said, I usually don't do many body physics, but I do a little bit of electronic social calculations. I couldn't resist just showing a little bit how this works. So this is a little moire Hamiltonian in 1 dimension, which has a density of states, the statistics of the eigenvalues, which is not completely trivial. So this I just computed using the diagonalization of a relatively large matrix and then some techniques with polynomials. It works pretty well. But what I can do is also use the randomized trace estimator that I was just talking about. Let's go back to, all right. It's always dangerous to do this live. So of course here, I took just exactly one vector. This R equals 1 is one vector to compute the trace. It's not fantastic, there's a lot of noise, but nevertheless we can recognize the shape pretty well for something that used only exactly one vector instead of computing a trace. And if I use a few more vectors, it gets better. And let's say with 50 vectors, I could be quite satisfied already that I did a good job of reconstructing the trace without having to compute the eigenvalues of the matrix. Yes?
Is this basically that Hutchinson algorithm? Or
Yes.
Oh, okay.
This is a Hutchinson trace estimator. Yeah. All right. So more generally, one of the main uses of the randomized numerical linear algebra has been in order to find low-rank decompositions, so of matrices. I want to stress this fact. So let's say that I know that I have some matrix of size m by n that for some reason happens to be of low rank, meaning that I have an approximation of it to some tolerance epsilon that has rank k, which is much smaller than m or n. How can I compute efficiently and have some kind of decomposition of this matrix AK, which can be much smaller to store than the full object? So given a Gaussian random matrix, so we take a random matrix where the entries are Gaussian distributed, and we compute the sketch, so we just multiply A with omega. So note that this random matrix is of size n by k, so it's actually pretty tall and skinny. Then it's often true that we can reconstruct the full matrix by taking the following product. So we have ymk, the sketch that we just computed, which has size m by k, so it's much smaller than the original matrix. And then this second piece over here with the pseudo-inverse, y dagger in this case, of size k by n over here. So there is a lot of excellent surveys on this topic. I list them here. I'm not going to spend too much time about this. There's a two-stage approach, let's say, to this low-rank matrix factorizations using randomization. So typically the first part is to find the range. So we want to find an orthogonal basis of the range of the matrix, of the columns. So let's say I have an idea of the target rank. So this is a little bit dubious sometimes. We have to have a good idea of the low rank that we want to achieve. And if we underestimate it, we might be in trouble. So usually we oversample a little bit. We go a little bit further. We go to k plus p. So we pick a random matrix over here. We compute the sketch, y, which is a omega. Then we compute a QR factorization. The object y is much smaller than the original matrix. So this is actually fairly cheap. The QR factorization is a good good numerical linear algebra object that we know compute in a stable and very effective way. And then now that we have an orthogonal basis for the range of the matrix, we can do lots of things. For example, we can compute, in this case, the randomized SVD. So we hit now our original matrix from the left with the basis Q star. So that brings it to a size which is now K by N. And we can compute a singular value decomposition of this much smaller object, compute the right-hand side, and now we have an SVD which was computed in a much cheaper way because we exploited the fact that we knew the matrix was low rank to begin with. So just to walk through the algorithm, actually when we compute the QR factorization in a kind of unusual step, we just don't care about the factor R, which involves all the randomness. What we care about is the tall and skinny Q, and then we compute the right-hand side. Here is another way. If we actually have already a factorization of our matrix, so if we know already a factorization of our matrix, so note that this is kind of what's going to happen with our tensor trains in a way. We already have some kind of factorization, and we want to compute a better one which reduces the ranks. So here I have a rank R approximation of my matrix, but I know that actually it's a rank K matrix, so I want to reduce this. Then I can do even a little bit better than before. I just have to sketch A in order to get a good idea of the decomposition. All right. Yeah, so here we can compare the randomized version of the algorithm to the deterministic version of the algorithm. In the randomized version, we are picking a sketch omega, making this y much smaller, and compute a QR and essentially be done. In the deterministic version, we have to compute first an orthogonal decomposition of the matrix A, then an orthogonal decomposition of the matrix B with QR, and then we do an SVD on the resulting factors RA and RB. So the whole thing is a bit more costly. So here are the counting of the benefits of the randomization for this matrix rounding. If A is m bar R, MB is n by R, and we are running to round K, essentially the benefit is to go from a cost which is m plus n, unavoidable, R squared, to R by K. So we still have a factor R in there. Of course, we have to do some matrix multiplication that involves R, but we are gaining from R to K, and if K is much smaller, that's a significant gain. And the other benefit is to shift a little bit the computational burden from the QR factorization to just a simple matrix multiplication, which works better. And another thing that will come back is that actually, if we know that we have, in the first place, not just one matrix of low rank, but a sum of low rank matrices, then the sketch of the sum is the sum of the sketches, and this allows one to just gain a little bit more than otherwise. So just to have a rigorous bound somewhere in this talk, I went and looked for the rigorous version of these theorems. I said earlier, often this works. Here we have a little bit of a better idea. So there is a deterministic bound first. So if we take the sketch omega 2 and omega 1, then we can estimate the error between A and the projection y times A. So this means that I computed my sketch y and then computed the QR. I find an orthogonal basis of the range of y. So if I missed any piece of the range of A in the sketch, then this will show up as an error here. And I see that the first part of the error is, of course, the pieces of the singular values of A that I will miss anyway, because sigma 1 being the dominant part of size K, And my sketch can only ever, at best, find an approximation of rank k this way. And this is the best we can do. And then there is a second piece, which is kind of the sketching part. And what we see is this plus is again the pseudo-inverse of the matrix, actually, in this case. So we see something here which could potentially blow up if we don't control well the randomization. But luckily, we have good theories for random Gaussian matrices. We can find bounds on the pseudo-inverse of these matrices, and this enables us to find this kind of bound here at the bottom, where now what we see is, again, this part here is what we're going to miss. So if our matrix is exactly of rank k, this is going to be 0. If it's not, then we're going to miss a little bit, of course. There is no way around it. So this one here, we cannot do better than that. But then we have this piece here, which is coming from the randomization. And what we see is that even if we oversample a little bit, if L is greater than K, then this is not going to be much bigger than 1. Right? So essentially, if we pick these randomized algorithms, this algorithm tells me the average, at least, is pretty good. All right, so now that we have an idea of the randomized methods for matrices, let's switch back and do a little bit of a review of the kind of operations I'm thinking about when I think about the Tensor-Train format. So I kind of repeat myself here. The goal is to explore a tiny corner of the full Hilbert space by exploiting these low-rank structures. And the idea will be that sometimes, at least for some of these one-dimensional or two-dimensional Hamiltonians, actually we have an idea of the ranks of the bond dimensions that we should be expecting. It's not always the case. For 2D systems, as far as I know, the situation is more complicated. And for quantum chemistry problems, which are actually the one I'm going to show at the very end of my talk, I don't know that we have a good idea of the ranks to expect, but it works in many cases because quantum chemistry, I guess, is nice like that. We shouldn't be able to solve some problems, but yeah, it works. All right, so Tensor-Train notation to come back. So Spencer, I'm coming back to a little bit explaining this notation maybe a little bit more detail. So we have this kind of expansions. The cores here are all three-dimensional except for the first and the last one. We have this diagram notation, or we can also look at it at kind of three-dimensional objects. If I select the values for I, j, k, l, m, I pick slices, so 2 vectors, and then matrices in the middle. And I can take the product and will find the entry of my tensor. So in my notation here, the kth core will be this txn for the tensor x. And it will have dimension Rn minus 1 by In by Rn. I'm not restricting myself necessarily to size 2, like in these pin chains, but like the cookie problem could have any dimension for the modes. There's a couple of core unfoldings that allow us to look at this in a kind of matrix notation. So when I look at this three-dimensional object, if you're doing linear algebra, you would much prefer to see a matrix. So you have a couple ways to turn this three-dimensional object in a matrix. You can take the slices at fixed values of the mode. You can arrange them horizontally. That's what I will call the horizontal unfolding. So this will have on the vertical, so the column dimension will be the row dimension is the rank on the left, and the other 2 indices have been merged. And then I have a vertical unfolding where the column index is now the bond dimension on that side, and I have merged the other 2 indices. There is a third way to do it if you take the modal index to be one of the dimensions you really want to keep, but I don't think I need it in this talk, so I'm going to limit the dimension to 2 unfoldings.
Well, can I ask a question? So your starting point is a given MPS, and then you review the matrices inside, but you have to know that from the beginning, right? Or not. This is where I don't really know, right? If I don't know what my state is, then
so
I'm getting an MPS, and then and then I reduce the matrix size.
So usually, for example, for something like quantum chemistry, you can start from the Hartree-Fock state, which is a well-defined state of rank 1. So it's very easy to start from that. For spin chains and things like this, I suppose you could also start from some midfield model, which will be of rank 1. Usually you add a little bit of randomness to it for reasons I will come back to in a minute, which are not the same that I'm going to do it. But anyway, so now that we have this format, maybe we want to do some operations on it. So again, linear algebra, so not necessarily what a physicist would do, but for me, if I see something that looks like a vector, I would like to be able to do a couple of operations to it. For example, I can just want to do a scalar multiplication, how to multiply this tensor. And one thing to notice is that you don't want to multiply all the cores, you just want to multiply one of them by the scalar, because in the product, otherwise you would be multiplying by a to the power alpha to the power L. And the second thing I would like to do maybe is a linear combination of vectors. And luckily, we have a well-defined way to do linear combinations of tensor trains, in that the core is expressed in this kind of neat way. For each index in, I can do a block diagonal decomposition. And so what I see is that this will sum the ranks of the two original objects. Maybe I also want to multiply entry-wise these two tensors x and y. There is also a formula for that. The cores are essentially, we take a Kronecker product of the two cores, and the result is that we are multiplying the ranks of these two objects. So if we keep it up, these linear combinations might actually grow the rank pretty fast. So that's sort of concerning. Another thing that we might want to do is to have matrices, like the Hamiltonian in our picture. So this is very classical. Linear operators on tensor trains, or matrix product operators, are written as another diagram like this. The cores are now usually of order 4, except for the first and the last one of order 3. We can compute the matrix vector product directly using a formula like this. So here we have for fixed values of the bonds, I'm going to be adding, summing over this index I prime n, which corresponds to taking a matrix vector multiplication at the core level. And what we see is that we are merging the two indices for the bonds on both sides. And so we are again multiplying the ranks. So if my TT matrix had ranks R prime n, and my vector had rank Rn minus 1, Rn, then I'm multiplying these two quantities together. So again, this is growing the ranks very fast. So what we want to do is to reduce the ranks as soon as we can. And the classical algorithm for that is called the Tensor-Train rounding. It's needed essentially after every operation that we do on the tensor train, be summing, applying a matrix, something like this. It will recompress, hopefully, the tensor back to its original dimension. A classical example is if I just take twice the same vector, the same tensor, I add the two, I just double the rank for no reason. So if I compress, I should be able to find the original ranks. At the very basic level, if I have two low-rank matrices, so essentially the basic example of a tensor train where I just have two modes, I'm summing two objects that have low ranks. I could represent this like this. It's exactly the formula for the sum. And my goal is to find a better low-rank approximation, and you can bet that these randomized algorithms might come in handy for this, because at this point, I'm just using a matrix. So how do we extend this to tensor trains, really the question. So first, let's take a look at the deterministic algorithm. The deterministic algorithm for rounding has two phases. In the first phase, actually, we do a complete orthogonalization sweep of the tensor. So we start from the rightmost one, and going down, we compute QR factorization. So we find an orthogonal basis for the range, iteratively all the way down. So only the first core will not be orthogonal. And once I'm done with that, I can move to the right and using the SVD truncates. So in some sense, this is sort of bad news because this phase, this QR phase on the top, is already very costly by itself. So even though I might want to apply randomization techniques to perform the SVD in a kind of cheaper way to do this second phase, essentially the cost was already incurred in the first phase where I'm doing orthogonalization, and this is not going to gain me much in terms of timing. Maybe shortly, because actually I think I'm running short on time. Essentially, what we are doing is performing SVDs on something which is structured in this way. So we have two cores, n and n+1. And then we have the whole rest of the matrix, which we can expand in a sort of structured way, left and right. And because we are at this stage of the algorithm where the left part is orthogonal from the left, the right part is orthogonal from the right, these two are actually orthogonal. And so I'm only need to consider the middle one in order to compute, to truncate the ranks efficiently and accurately. All right, and to finish on this kind of review, how do we solve the problems of interest? So let's say I want to solve a linear system or an eigenvalue problem using this format. So the classical way is what we call the alternating least squares. The physicists call it DMRG. So we solve local problems, something like this. So I have my matrix in the middle. I have my tensor in black. And what I'm trying to do is find the tensor that will approximate, say, the lowest eigenvalue. So I want to minimize the Rayleigh quotient, x transpose hx, which can be expressed in this diagram like this. And so practically what we do is we sweep the tensor, we freeze a number, so either all but one or all but two of the cores. If I say in this example, I take two of them, everything is frozen, so actually I can compute essentially this looks like a matrix with four indices merged on one side, four indices merged on the other side. It's a large eigenvalue problem. I can solve that using some iterative procedure. It's classical, Lanczos, maybe a Davidson algorithm. And then I will obtain some big object that spans these two cores. I will truncate it using the SVD, and then continue sweeping to the right, sweeping to the left, and I will iteratively converge to the solution in many cases. Sometimes this procedure actually gets stuck in local minima, and this is why there is a whole business of introducing additional noise a little bit, randomizing in order to try to escape these minima. So what about the classical techniques? Why are we not using just the algorithms we know and love that enable us to solve eigenvalue problems? For example, the Lanczos algorithm, right? Very classical. I just need to be able to apply the matrix, so I know how to do that. It looks like this, slightly maybe unfamiliar way of writing it. I compute a Rayleigh quotient first, and then I compute directly kind of the orthogonal component of the vector. I continue like this, and I will get a triangular matrix, a tridiagonal matrix over here, and the basis vectors of the Krylov space. The Ritz values of this decomposition are known to converge very fast to the extreme eigenvalues of my Hamiltonian. In exact arithmetic, this would build an orthonormal basis. It's known to be slightly unstable, even kind of normal circumstances. But of course, what's the problem is that I'm doing global operations on my tensor at each step. I'm doing here, I'm applying my matrix, and then I'm doing a linear combination. And then I do the same thing at each step of the algorithm. And so this is going to grow my ranks very fast. And as we'll see in the examples from quantum chemistry, actually the ranks of the matrix are so high that even applying it once may be too much. So maybe that's why we're not using Lanczos. The problem is the rapid rank growth in the vectors of the basis that I'm growing. So luckily, there are some opportunities here for randomized low-rank approximations. So remember this sketch where we had two cores and then the rest of the tensor expanded. So if I have the left and the right part to be orthogonal, like I do when I'm doing my traditional algorithm, then I can use the traditional randomized low-rank approximation in order to factor A and B transpose into something of smaller rank. If Q is orthogonal, but Z is not, then I might want to use some range finder. And finally, if nothing is orthogonal, there is still some solutions that we will see in our experiments didn't work so well. So again, what we see is that we are going to hit this with a large matrix on the right, this randomized sketch. And what we do, of course, is that because we have tensor trains, we might want to structure our sketch as a tensor train itself. So we get this randomized tensor train on the bottom. These contractions here will be what makes the algorithm works.
So,
yes?
Can you remind me, like, is omega like Gaussian random vector originally?
So originally, in this picture here, I would like this omega to just be some Gaussian random matrix.
But now it's Gaussian random
yes.
locally in the MPS.
So now, of course, the cores are going to be Gaussian. And that means actually that all this nice theory that we have about random matrices will not apply. So we are not able to do much theory about this, except that it works.
So if it is locally Gaussian random, is it also globally Gaussian random? Or is
no,
it not?
I don't think so.
Oh, okay.
Yeah.
But we can hope it still works.
We can hope it still works. And so very briefly, the sketching algorithm will have two pieces. So again, there is a part of sketching, which is a sweep from the right to the left to compute matrices Wn that correspond to sketches. So this is actually fairly efficient because we have here our randomized sketch, which will work. And so here is the algorithm. We randomize first, and then we orthogonalize. So we have the sweep from the right. This corresponds sort of to the QR step. We have a sweep from the right to the left. But we don't have to orthogonalize anything. And then from the left to the right, we compute QR factorizations on small matrices. And we obtain immediately a much reduced version of the tensor train. One catch is that we have to somehow guess the right ranks that we want to compress to. We're not able to find them adaptively. There's a version of this that does two-sided sketching, avoiding a little bit of orthogonalization, but we found that it actually doesn't really improve the performance. And so to sum it up, we have three strategies. In orthogonalized and randomized, we just use randomized methods in order to compute the SVD in an efficient way. We have the randomized and orthogonalized, where we first do the sketching from one side and then compute randomize the projections, and finally this two-sided way. So here is the results, in some sense, on kind of synthetic examples. So if we pick a perturbation of our tensor, which is not very differentiated from the actual ranks, of course, the randomization kind of struggles. There is not much difference between the singular values of the perturbation and that of the tensor. So which one does the best? So the TT rounding is perfect, but it's deterministic and expensive. The orthonormalized and randomized and orthogonalized actually do essentially the same on here. And the worst is this two-sided, which is on top over here. If the perturbation gets to be very small, they essentially all work pretty well. And what we observe is that the speedup is the best for this randomized and orthogonalized. It's not great. We get this speedup of 5. So there was a lot of effort for not much. So luckily, there is still hope. So one thing that this is actually good at is if we're trying to round something which is structured, like for example, one of these linear combination I was talking about, then we don't have to form the linear combination. Remember, it has this kind of block diagonal form. We don't have to actually assemble this matrix which has full of zeros. So in this case, actually, the randomization will be very efficient because we can do the sketches just using the sketches of the individual summands. And then we'll have an algorithm to find an approximation of the whole thing. So if we go to this cookie problem, I'm not really interested in the results as much as whether the algorithm worked. In this case, the bottleneck, because I'm using the GMRES iterative algorithm to solve the problem, I have a Krylov algorithm, I have linear combinations. So actually the bottleneck were this sum of matrix product states. And what I find is that this works pretty well. I reduce the runtime from about 1,500 seconds to 100 on my laptop, depending on the number of parameter samples. Yes.
Can't you also use the alternating least squares?
Of course I could.
Yeah, but
Of course I could.
how's the performance?
But in this case, this is the goal would be with this we can solve problems that are not symmetric. Right, so sort of the DMRG for one can get stuck in local minima, and it's also limited to a problem where the matrix is Hermitian.